Get up off of that thing. Come on now, let's do it. So let's finish this hypothesis test, or at least, actually, we may not finish it in one more video, but let's still keep going on it. So far we've talked about our data, what it means, what it implies, what we're trying to test, and here's our expected values, which under the null hypothesis is what you thought you were going to get. So to make a test statistic, like a z-score or a t-score, it's going to end up being different. It's going to end up being a chi-squared score. Let me remind you of how we used to do it. We would take our data minus what the null hypothesis thought we were going to get, and then this was an error term that said, okay, is this difference big or small? What does big or small mean? And some measure of that error. So we're going to use that same idea here. Instead of x bar, I have data here. So my equation is going to say my observed value minus what I thought I was going to get from the null hypothesis, which is this guy right here. Observed value minus an expected value. And we want to divide it by some measure of, is that a lot? For example, 54 to 48, that's a difference of 6. And 7 to 12 is a difference of 5. But 7 is a lot smaller, so maybe a difference of 5 means a lot to 7. A difference of 6 when you're as large as 54 may not mean a lot. So we want to divide by these kinds of numbers so that we can measure, is this difference big or little comparatively. If you're going from 3 down to 1, that's a huge drop. But if you're going from 103 to 101, that's not a very big drop. There's mathematical reasons why it's helpful to do the square root of the expected value. You might argue, how come we're doing the square root of the expected value, not the observed value? Well, the answer is the expected value, according to the null, is the better number. This number has error due to bad luck. This number is correct, says the null hypothesis. So we're going to divide by the square root of the expected value. And that's great. This right here is a great test statistic, but we're going to end up doing that for every one of these guys. And if we want to add them together, we've got a problem, because you cannot add standard deviations. End of really unfortunate story. So I can do this for every one of these cells, but I can't combine them into one thing unless I remember that you can combine variances. That's because the normal distribution wants e to the negative x squared, so we can add things that are squared, and we do want to use some of the normality results here. So this guy right here will work if I square him, which gives us a simplified form of the equation. Notice it's observed minus expected squared, but if you switch that and you do expected minus observed squared, then it's the same thing. In class, I mix it up all the time. In videos, I pause it and fix it if I ever mess it up. Sometimes this equation is written as observed minus expected squared over expected, just because it's a little easier to write without all those extra letters. What do we get from this? Well, we get what's called a chi-squared if we have enough data. How much data do we need? There's lots of different rules people have. We are going to use the absolute simplest rule. I need every expected value to be bigger than 5. So let me go to my expected value table. 10, 12, 9, 7.9, there's my smallest one. None of them are below 5, so I'm okay. If any of them are below 5 in this expected values table, then quit. It's a cannot do and just stop. You like those questions because they're easy. You just put cannot do for everything and you're done. Up here, it doesn't matter if it's below 5. It's possible to have an observed value of only 2, but still have expected values over 5. And don't fall for that. If you do one of these problems where you cannot do it, and then you get all those red X's and web assign, and it just makes you feel silly, like toe shoes. To do the chi-square test, we need to know our degrees of freedom. What are the degrees of freedom? If I knew these totals, how many of these would I still have to actually calculate, right? So for the expected values, we had to calculate this guy and those guys, but we didn't have to calculate the last row because we knew the total. We could have just subtracted them. That's not the way we did it because this is a video where I'm teaching how to do it, but if I knew these, I wouldn't have to do the last one. So how many do you have? If you have a huge table, 7 by 9, what you would do is you would take away one row and one column, and how many cells are left? So the degrees of freedom are row minus 1 times column minus 1. In our case, can you see that? Does red show up? It shows up possibly well enough. Let me write it bolder in black. Degrees of freedom, row -1, columns -1. In our case, we have 2 rows and 4 columns. So that would be 1 times 3. Our degrees of freedom are going to be 3 in this case. There's 3 cells that you have to calculate. The others, you could choose to get them just by looking at the addition. Okay?